So we're trying to create a sampling distribution so that we can take samples and extrapolate to the greater population. So our sampling distribution is the distribution of all possible values that can be assumed by a sample statistic, and we're computing that from samples from the same size. So we're taking a bunch of different samples the same size, and we are randomly drawing them from the same population to better understand that population parameter. So if we're trying to understand what is the average age of people in Alberta, we take a sample of people in Alberta, we calculate the sample statistic, so that's the average age of the people in Alberta. And we do that, and we recognize that if we took a different sample with different people in it, we would get a different average age. All trying to better understand what is the actual average age of the population. So what is the population parameter, the age of people in Alberta? Now, we use different symbols to represent the difference between the parameters and the statistics. So while we can find the average age of all people in Alberta, or of our sample, to differentiate between the parameter and the statistic, we use different symbols. So the average for the population, we use the symbol mu. That's this Greek symbol that you see right here. Here we go. Whereas if we are finding the average for the sample statistic, then we use x with a bar over it. So we call it x bar. Now, if we're looking at proportions, so percentages who fall into certain categories, then for our population parameter, we'll use the lowercase p. And if we are looking at a sample statistic, we might use a p hat, for example. For standard deviation, a common nomenclature is that the parameter is a sigma, and for the sample statistic, it is an S. So standard deviation S is for the sample and sigma is for the population. Variance, since it's just standard deviation squared, is either sigma squared for the parameter or S squared for the statistic. We can also look at correlation. So we'll have some videos coming up looking at correlation. This is how much when one variable moves, does the other variable move in the same direction? Does the variables move in opposite directions? Or maybe they aren't related to each other at all, in which case the correlation is 0. So when we measure correlation, we go from -1 to +1, 0 being no relationship, 1 being when it moves, the other one moves identically in the same direction. -1, when one increases, the other decreases by the same amount, or anything in between. When we look at correlation, the population parameter, we use the Greek symbol rho. So it looks kind of like a P, but it's actually a Greek symbol. And if we're looking at the sample statistic, we use an R. Okay, so different nomenclature to help us differentiate whether we're talking about the sample or whether we're talking about the parameter. And remember, our sample statistics are trying to estimate those population parameters. So we assume that parameter is a fixed value, but it's unknown. So we take samples, we get statistics. Those statistics give us lots of different numbers, and we create that sampling distribution to kind of help us figure out where that population parameter might actually be. Okay. So let's look here at an example. In 1990, the average age of first intercourse for a sample of female teenagers was 17.2 years. What is the population in this example? Well, the population in this example is female teenagers, all female teenagers in 1990. The parameter in this example is going to be their average age, but we don't know the true value of that average age. So what we do is we take a sample, we, let's say, interview or survey a handful of female teenagers, and the average age they report becomes the sample statistic. And depending on who is in that particular survey, you're going to get a different average. So the statistic is going to change from sample to sample. We can have our parameters and statistics be proportions. So here, only 35% of a random sample of 1,024 adults in the US in June 2001 thought that a genetically modified food was safe to eat. What is the population in this example? Okay, Here we're talking about adults in the US in June 2001. The parameter in this example is going to be a percentage, and it's the percentage who think that genetically modified foods are safe. That's going to be for all adults in the US. The statistic is going to be the proportion in the sample. And so if we're looking at this example here, the parameter is going to be P, and the sample statistic is going to be P hat. And if we're looking at the average, the sample statistic is going to be X bar, and the mean for the population is going to be mu. So you need to be able to identify what is the population of interest, how are we summarizing that population of interest, that's the parameter, and then what are we going to use to try to estimate that unknown parameter, and that's going to be the sample statistic. So we're trying to make statistical inference. We're asking questions, making judgments about the population based on the observed statistics from the sample. And there's two main ways that we do the statistical inference. One is what is called confidence interval. This gives us a range. So we think that true population parameter is somewhere in the middle of this range. We have a high value and a low value. It's somewhere in between. And we create a level of confidence. How accurate are we? How confident are we that the parameter lives somewhere in between those two numbers? Okay, so we're going to talk about in some future videos. We'll do some confidence intervals. We're also going to do hypothesis testing, the alternative method for statistical inference, which is going to be that we are going to make a statement, a null hypothesis, and an alternate hypothesis. And so we might say, okay, well, we think that these two groups are the same. That's the null hypothesis, that the average age of these two groups is the same. The alternative hypothesis is that the average age of these two groups is not the same. And so what we're doing is we're making a statement about the population parameter, the average age. And what we're going to do is use our sample and relate it to our probability distribution in order to see whether or not we can reject the null hypothesis and say, yes, that sample is so different that the true underlying population has to be different, that the average ages are not the same. Or is our sample statistic giving us two average ages for our two groups that is close together, that it could just be sampling error, they're not a big enough difference, and so we fail to reject the null hypothesis, and it's quite possible those two groups do have the same average age. So that's how a hypothesis test works. Okay, so all of this is taking our sample information, trying to make estimates about the population parameter, trying to extrapolate to that greater population. We can do that with confidence intervals or with hypothesis testing. Okay, and we're going to have videos going through each of those as we move through our statistical inference process. But the first thing we're going to do is we're going to look at a sampling error and building our sample distribution.